All right, welcome back. Hope you had a good weekend. It'll be raining less this week. Okay, so we were talking about quantum channels. And there's a very important theorem that we're going to talk about now. We've talked about purification of states. We talked about Neymark extension theorem. You could say it's purifying measurements. Now we're going to talk about purifying quantum channels. So this is called Stein-Spring dilation theorem. Stein-Spring was a mathematician who published this paper in 1955. And I think maybe it was, I think in the 70s that people started realizing the relevance. Well, I don't want to speak for people, but you know, the importance of it was used in 1975 to prove what's called the data processing inequality for quantum relativometry. We'll get to that later. So it's important was at least recognized then, right? And then many years later, like in the mid 90s and 2000s, it was realized to be fundamental for quantum information processing. Okay, so to talk about this, let's first recall the Krauss representation. So this is that every channel, its action on an arbitrary operator, which, you know, if you're thinking in a physical context, X is going to be a density operator. It can be written as this linear superoperator. The fact that the KI's match on each side corresponds to the map being completely positive. We already talked about that. And then there's the condition that the sum of the squares is the identity. And that corresponds to it being trace preserving. Okay. So the Stein-Spring theorem is that every channel can be realized by, and you should really think that it's just kind of a unitary interaction on a larger Hilbert space. Okay? And there's going to be an environmental system that interacts with the channel input system, and that can realize the channel. So it's really three things. One, tensor in an environment state. Right? So I'm going to call the environment E prime. We want to allow the channel input system and the channel output system to be different dimensions. And so that means we have to allow the input environment and the output environment to be different dimensions as well, so that overall the interaction is unitary, because a unitary is a square matrix. Okay, so you tensor an environment system, apply unitary. So the input of the unitary is A and E prime. And the input is the original channel input and the environment system that you tensored in. The output will be channel output and another environment system that I'll call E. So we just need different labels for the environment. We use E prime and E. Okay. So let's label all these. Channel input, environment input, channel output, I'm trying to abbreviate these things, and environment output. Okay, and then final step is trace out. Okay. So I think I said that purification is one of the most important theorems and concepts in quantum information theory. This is directly connected to that. It's the dynamical version of it. And I would say, after you take this course, if you don't do research in quantum information, you're going to forget a lot of stuff, right? That's just how life is. And so I would say, this is probably one of the most important things to remember from the course that distinguishes quantum information processing from classical. The fact that we can do purification. Okay? So let's draw a diagram of this process. Here comes the input, rho A. Here's the environment. Here's U, unitary U. And here's the trace out. And what we're saying is, adjust the diagram slightly. Put a box around this whole thing. And this is an identity. The channel can be realized by this process. And this is similar to the interpretation we gave of purification. We said purification allows us to interpret noise in a mixed state as being due to entanglement with an inaccessible environment. Okay? So now we're extending that interpretation to say that noise in a channel, right? Like if I'm trying to transmit a signal using a cell phone from one place to another, and there's some kind of corruption of the signal, we can think, as counterintuitive as it might be, but we can model the noise as being due to a unitary interaction with an environment. And that unitary can entangle the input system with the environment. And then the noise that you see in the output, the corruption of the signal, is due to not having access to the environment. And anything you don't have access to gets traced out. Okay? So that's how you can think about it. Let me give you an example. Let's state this in mathematical terms first. So it's kind of crossed, and we can figure it out. So this is what we're saying mathematically. Okay, and then there might be a question of how large do you need the environment E to be? I think there's a little typo in the notes. The dimension of E, system E, has to be greater than the Choi rank of the channel. Remember, the Choi rank is, you form the Choi operator, which you get by sending in one share of the maximum entangled state. The right gamma means unnormalized. That makes a positive semi-definite operator, and then you compute the rank, and that's the size of the environment you need. Okay, before we proceed further, I want to, yeah.
E prime has dimension one, or you only use one dimension in E prime.
Oh, no, we need more. The point is that the E prime is initialized to that state, but you need a larger space. Yeah. So like, okay, so we need dimension for this. All right, so like we at least need you're trying to satisfy this, right?
That was the origin of my question.
Yeah, right.
That was that again was the origin of my question.
I see. Yeah. And it should be possible to satisfy this equation. And you need this to be satisfied as well.
That must be satisfied.
This must be satisfied. Yeah, the environment has to be, at least the dimension of the output environment has to be at least that size. Okay, let me give you an example so you can try to think about this physically. It's a nice example. From quantum optics. Okay, so this is often called pure loss channel. Pure loss channel, because the only noise in the channel is due to loss. Okay, so this is a beam splitter. Experimentally, it's just a half silvered mirror, and you can input laser light to it in one port and another, and then the light will either transmit through or reflect. And there's a parameter eta between 0 and 1 that's called the transmissivity. Okay. And in this model, this is going to be the unitary extension of a loss channel. That's what we're showing. Okay. This is the most common model used. So this is the input, the channel input. This is the channel output. And this is the environment input and the environment out. Right? And if the channel is a pure loss channel, then the state of the environment is initialized to the vacuum. So that means, 0 photons present. When I write this 0, it's different from the 0 that we write for the computational basis. This really is meant to be the photon number basis. And this is the vacuum state. So in this model, eta is the average fraction of photons that make it from the input to the output. Okay? And this is a model of loss for communication in free space or communication in an optical fiber. There'll be different ways that eta behaves. If you're talking about free space or a fiber, but this is one of the most important communication channel models in quantum information theory, and all of its capacities are known now, which is a nice thing to know for such a practical challenge. You can study its classical capacity, its quantum capacity, and many others, private capacity. So, the channel is from here to here. There's a way that you can write this. You can write down the Krauss operators. There's an infinite number of them. I actually didn't prepare that part, so I don't know them off the top of my head. But they're a function of just theta, and you can write them down in the photon number basis, how they would act in the photon number. Okay. There's also a way that you can describe this in what's called the Heisenberg picture. It's much simpler to do so. We can use a relation between, this is easy to write down, so I'll do this. We haven't talked about creation and annihilation operators in this class. But some of you will be familiar with that. Let's call this E prime E prime to be consistent with the notation that we're using here. So this is a simple mathematical model of a beam splitter, and it tells you how operators corresponding to the input and output modes change as a consequence of this evolution. So rather than describing things in terms of the state evolution, you describe things in terms of the operators. So I'm not going to say too much more about this. Yeah. But indeed, you see it's very similar to this diagram. Like, what did I do? I put a vacuum state here. Instead of a U, a general U, I put a beam splitter, right? And then, we trace over this environmental output to get the channel output. Okay. And I would say it's a topic of research interest to figure out practical methods of communication over this channel. There's still work to do there. Yeah.
What if fix the picture?
No, you still have this. We're going to get to that. You could do a unitary in the environment, and then up to that, it's unique, right? So that's how it is with all this purification business. Up to an isometry on the purified system or the environment system, you have uniqueness. Yeah. Okay. Oh, there is one thing else I wanted to say. We talked about amplitude damping channel and erasure channel, right? So something that's very interesting is if you limit your input space to a finite dimensional subspace of 0 and 1 photons, the resulting channel, I would say this induces an amplitude damping channel. That's one that we talked about already. Right? We talked about the Krauss operators. This is also called a passive device. It does not increase photon number. Photon number is preserved. So whatever the total photon number of the input and environment is, the total mean photon number of the output and the environment output will be the same. Okay, so it's energy conserving process. And so that's an interesting way you connect back to the previous channel model that we studied. I think last time we were discussing about, I mentioned dual rail encoding. I can't remember if you were asking or someone else was asking. We talked about, I mentioned dual rail encoding. So if you use this channel twice with what we'll write it, dual rail encoding. So this is in the first node, you have 0 photons. In the second, you have 1. Or in the first node, you have 1 photon. In the second, you have 0. So you restrict your input space to the span of this. You're talking about state vectors. Okay? And what will happen is that this encoding induces an erasure channel. How do you think about that? Well, if the transmissivity parameter is eta, then the probability that a photon makes it through is eta. That's another interpretation of eta. Okay? And so the probability that the photon does not make it through is 1 minus eta. That's going to be the erasure parameter, right? So if I send this state through, 0 will go through on the first channel use. Nothing always makes it through, right? 1 will have a probability eta of getting through, and with probability 1 minus eta, the photon will be rerouted to the environment. It'll be lost, and the output will get the vacuum. So the state in that case will decay to 0, 0. And that's the erasure symbol, right? The erasure symbol is orthogonal to both of these. So let's write that down. The erasure symbol is 0, 0. Sorry, it's a bit small at the bottom, but I'm writing erasure symbol is 0, 0. Okay, and then similar with this, because you're using the channel twice and you're modeling it as the same channel with the same transmissivity, the same thing happens. If you input 1, 0, the photon makes it through with probability eta, and otherwise the the output gets 0 with probability 1 minus theta. And you can show that's kind of the intuition behind it. You can show mathematically that it leads to the erasure channel precisely as we defined it. So your input alphabet is 2 symbols. Your output alphabet is 3 symbols. The original 2 plus the erasure symbol. Okay. So that's how these qubit channel models connect to something quite practical. Right? Okay. So I want to talk about the theorem in more general terms, and the proof will be very simple, like it was for the name mark extension theorem. We just, in that case, gave a particular construction and proved that it worked. We're going to do the same thing. Okay, so let's recall, and let's work in the state vector picture. Let's model the input as a state vector psi. And then we're tensoring in an environment state vector E prime, and then we're doing the unitary, right? So remember we talked about the process of tensoring in a fiducial state of the environment and then doing a unitary is equivalent to an isometry, right? We already talked about that in the context of measurements. Let's write the symbols. I think that can be helpful. The induced isometry is from A to B and B. Right? So we can also write this statement over here in slightly simpler terms, saying this. B, X, B dagger. Right. So fewer symbols, but then we have to know it's an isometry. We're using a shorthand. Okay, so what is the proof of the theorem? It's just going to be set. It's a K, what we could call canonical isometric extension of a channel. Okay. You take the Krauss operators, we've written them previously, they're KIs. And then you tensor in with those state vectors to the environment. That's the basic idea. Okay. And remember, in the context of measurements, we did a very similar thing. For the POVM, we took the square root of each POVM element. And then that was the construction that we made. Okay. So we can prove, so we want to prove 2 things, that this equation holds and that this is an isometry. Okay, so check isometry and check. Okay. Another comment to make is the Stein's-Frick theorem, we're talking about one of the physical interpretation in terms of the unitary, right? Because an isometry might seem like an abstract mathematical thing. So, but the argument there is, remember, an isometry is a rectangular matrix, and a unitary is a square one. So we're picking some of the entries like this, and the other ones you can fill them up in whatever way to make it a unitary. Okay, you just have to ensure the conditions of unitarity are met. The conditions of unitarity are met. But all that's going to matter is how, when the environment is initialized to the 0 state, how U acts in that case. And this initialization is what ends up picking off some columns of the unitary matrix to be the rectangular matrix for the isometry. Okay? So check isometry. Let's do that. V dagger V. Dagger. Tensor Right? So that's V dagger. And V is, as we wrote it. This is very similar to, I think we already essentially did this calculation before. This is a delta function. Technically, this is a scalar, so the tensor product is the usual product. So that's a delta function, and then we get this. And then from the original assumption that n is a channel, this will be sum to the identity. So that's the proof of part one. Okay, let's check the extension part, right? So right. Oops. Okay, and then when you're faced with this, it might seem a little tricky. If we write system labels, it might be helpful. These KIs really act on the incoming A system and take it to a B system. Right? So I'm going to write this, all the steps here. You have to, it might be a little tricky, like how do you combine it? Right? Okay, so it can be helpful to think about the dimension of the matrices involved, right? Like each KI is a rectangular matrix. It's dB by dA, right? And then these are vectors, they're dE by 1. Okay? And so overall, this matrix together is dB by dB times D by dA. Right? So, and then XA is dA by dA. And then this right here will be the flip, right? And so, you know, the mathematics is fine, right? Question is, where does the X go? So, you know, this vector, the incoming system is one dimensional. So it's like it doesn't act on XA. The point is that KI acts on XA, okay? And then you tensor things together. So the next step, you know, when you're first doing this stuff, let's see, we'll check. The next step is this. Dagger. And then this. Fine. All right. That's how they combine. And then you have a trace over the environment. So I'm not going to show the next step in detail, but the next step is kind of the thing we've been doing a lot. The sum comes out, the partial trace goes in, and then this ij collapses to a delta function. So it reduces to precisely what we want. And then, you know, that was the Krauss representation of the channel. That's it. Okay, let's now address the point that Vermeil was hinting at, which is the uniqueness of isometries. Right? So let's do that. It's going to be similar to what we did for measurements, but I think we should still do it. So you can kind of see it in this diagram, right? If I were to sneak in an isometry here, called W, going from E to E double prime, and then I do a trace, it's not going to, the statement will still hold, right? We talked about a cyclicity of partial trace. That's what we can apply here. You know, when you're doing this, you're not really changing any information in the environment. You're just like doing a rotation, and then if you trace over it anyway, it doesn't matter, because all that we need for this equality is the overall channel from input to output is the same. So, so let's write down the slogan. Every channel purification. We also call it, the technical term you'll see is isometric extension. It's related to isometry acting on the purified system. So that's the slogan. And proof of it is pretty straightforward. We'll let P and E an isometric extension of M. Okay. And the one part of the theorem that we're showing, we're not showing the other part. What we're saying is that W going from E to E double prime. So first this, then W, as depicted in this diagram, is also isometric extension. So how do you see that? Well, just a few lines. We start out and we suppose that V is an isometric extension. So we suppose that this equation labeled as star on the left holds. Then we want to figure out if this is an isometric extension. So we do partial trace with E double prime. And I think I will skip the system labels to make the equation shorter. All right. So then we use cyclicity of partial trace. So actually that's where the writing the identities explicitly in the system labels actually would help. So for that purpose, think about this diagram. Right? Like, we're tracing over this, and system B is not being traced over. And so, like, there's an implicit tensor of W with identity on system B. Okay? And so we can wrap this around. When we do so, with the partial trace over E double prime becomes a partial trace over E. Right? And by assumption, W is an isometry, so W dagger W is identity. And then that's pretty much it. Okay. And then there's a converse part that holds. I haven't been proving the converses of these things. But the converse is, suppose that V is some isometric extension and V prime is some other isometric extension of the same channel. Then what you can show is that those isometric extensions are related by an isometry, taking the environment of one to the environment of one. So like, this is the only way that you get isometric extensions. You get one, and then you generate all the others with is whatever W you want. Okay.
And you also have isometrics to the equal dependent.
That will change. Oh, E prime. That's a good question. I feel like that could change the channel. What's that? It would change the channel. Think about this. So I can give you an example where it does change the channel, the beam splitter. Right? So we talked about the beam splitter. So we talked about one channel where we input the vacuum. That's an isometry, that takes one orthogonal basis to another. So we could take the vacuum to single photon state. So that's a very different channel, right? One of them is called the Gaussian channel, because it can be, you talked about that. It can be described in the formalism of Gaussian quantum information. But a single photon state is very different from a Gaussian state. It'll generate a non-Gaussian channel. So it's very different. Yeah. But I mean, there could be a different isometry that would preserve the vacuum, right? Like you could have an isometry that would take vacuum to vacuum and 1 to 2 and 2 to 3. And then if you did that, the channel would stay the same. So, but the uniqueness theorem is this way. Okay. All right. I wanted to talk about some other channel models that come up. Any questions about this? Because we're about to progress to kind of a new discussion. Pauli channels. These come up a lot in the context of quantum computing. Different course. You imagine a qubit input, and randomly one of the Pauli operators gets applied. The Paulis are Hermitian, so we don't have to put daggers on the right side. One of the Krauss operators in this case, they're going to be root pi, identity, root x, etc. And then you can do things like take an isometric extension, but you just use the canonical construction. Right? What's the size of the environment for a Pauli channel where the probabilities are all strictly greater than 0? Like a little quiz question. What's this? So if we take an isometric extension of a Pauli channel where all these probabilities are strictly greater than 0, what's the minimal size of the environment? Four is correct, yes. So the canonical construction would be this. You put a label and then that. And then you can check this with the statement we said about the Choi rank, right? If you act on one share of a maximum entangled state with the Pauli operators, that's like what we did in superdense coding. So you'll get the 4 Bell states, and you'll be summing up their projections, and it'll have rank 4. Because those are, the Bell states are all orthogonal. Okay. So there are special instances of this that are interesting. One is called the dephasing channel. You can also refer to it as a decoherence channel. You hear this term decoherence. Decoherence is kind of a confusing word. Sometimes people use it to refer to all kinds of noise, but it's really meant to be what the word said, decoherence, right? So like if you have a coherent superposition, there are off-diagonal elements in the density matrix, and if those are decaying towards 0 by some action of the noise channel, that's a decoherence channel. You're going from a coherent superposition to an incoherent mixture. Right? So what is a simple example? Rho goes to 1 minus p rho plus p. And then you can show in the standard basis, that these off-diagonal elements will decay as p increases to 1/2. When p hits 1/2, it zeroes out those off-diagonal elements. Okay, so those are things you can show. Yeah. And this is a model of noise. It's a simple model of noise in superconducting qubits. We talked about how amplitude damping channel is, if you go to experimental talks, they talk about T1 time. At least it used to be the case when a decade ago, people were worried about getting a single qubit. Not really the case anymore. But T1 was the relaxation, like how long before an excited state decays to a ground state. T2 time is related to this channel. So it's, if you were to prepare a superposition of 0 and 1, how long before that decays to one of the two possibilities, before the superposition decoheres to one of these diagonal sectors. That's its relevance. When p equals 1/2, that's a classical channel. So we should say that. When p equals 1/2, it's called a completely dephasing channel. Or even a classical channel. So why is it called classical channel? Well, let's write this out. If this is your initial state, when p equals 1/2, it will go to. And so it's called classical channel because only these classical states on the diagonal can be transmitted. Quantum information cannot be sent through. Okay. And typically the capacities of this channel and the erasure channel are much easier to study and analyze. Okay, polarizing channel, that's another example. This is where the X, Y, and Z probabilities are equal. Okay, and so if you think in terms of the black sphere, it's like the state is always going towards the maximum mixed state, going towards the center of the sphere for the polarizing channel. So what is the channel? We have a single depolarizing parameter, 1 minus p. And uniform probability for the other possibilities. This is one way to write it. I don't know if we talked about this identity yet. So this is an identity that holds. If you take an equal mixture of Pallies, and this is, it makes the maximum mixed state. Okay. One of you had this for homework assignment. Maybe Roy did. We talked about something like this. Maybe I'm wrong. So that's an identity that holds. That's the case in which all the Pallies are set to be the same. Sorry, all the probabilities are set to be the same. This case is called a completely depolarizing channel. Okay. Why is it called that? The action of this channel you can draw in terms of this diagram. It's equivalent to tracing out the input and replacing with the maximum mixed state. So that is literally cutting the wire and replacing with random noise. That's the worst possible channel. It has no capacity for anything. It's completely depolarizing and it's completely useless. Okay, so, but it's useful to have this as an analytical tool. Okay, one thing you can show is that by using this identity, right, we can use this identity, add in the identity term and a 4p over 3, divide by 4, and like rearrange things. And you can rewrite the polarizing channel like this, where it's maybe simpler conceptually to think about it. And in order to have the interpretation, so this will work. This is actually a legitimate channel for any p between 0 and 1. But we can have an interpretation of it that with this probability, the state gets through, and with this other probability, the state gets trashed and replaced with the maximum mixed state. However, that interpretation only holds if 4p over 3 is less than 1, right, in terms of a probability. You can prove that for any p between 0 and 1, this is a completely positive trace preserving. So it's a legitimate quantum channel. It just lacks the interpretation in terms of cubic getting through or being replaced with the maximum mixed state. Okay. This channel has been a puzzle in quantum Shannon theory for a long time. It's very easy to write down, but no one has figured out its quantum capacity. This has been open since the dawn of quantum Shannon theory. And people have tried to work on this for a long time. In fact, when I wrote my NSF career grant proposal, one of the comments was, why aren't you trying to figure out the quantum capacity of the depolarizing channel? I was like, why is that on me? Why can't I do other things? So anyway, that's an important problem. And, at the end of the semester, you'll have to do the final presentation. That would be a topic of interest, right? We have to start getting in the mode where y'all are thinking about that. That'll be like the last week of the semester. So you should start thinking about what you want to present. You can suggest ideas to me and we can see if it's something reasonable. Okay. All right, we have about 30 minutes left. I have some other things in the notes for lecture 12, but I think I'm going to just skip it. And we can start talking about quantum teleportation, right? Which is like wonderful insight, one of the earliest insights of quantum information, 1993, Bennett et al. I'm going to see if I can name the inventors. It was Bennett, I think he was on it. Perot, Joseph, Wooters, somebody else. Anyway, the Nobel Prize in Physics will be announced tomorrow, right? And there's always chatter. Like maybe one year they'll go to teleportation. But I've seen people saying they'll go to experimentalists first. Like Zeilinger, Alain Aspect, and Bowser. Those are the names I've seen for quantum information stuff. But Zeilinger did some of the original teleportation experiments. Okay. Okay, so this is probably the most remarkable protocol in quantum information. It's very simple, and it's the basis for many other protocols and many more complex protocols in quantum information. It gets used in quantum computing, of course, in quantum communication, quantum key distribution. It gets used there. There are ideas based on it there. Yeah. So many of the ideas in quantum information kind of boil down to, you can like re-understand them in teleportation. If you're sitting in a seminar in quantum information and you're clueless, but you want to sound smart, you could ask the speaker, how can we understand what you're doing in terms of teleportation? And then you would, it's likely that that's a good question. Yeah. So, all right. So why is it so remarkable? So we can combine, it allows for combining classical communication and entanglement to realize quantum communication. Okay. So the thing is, classical communication alone cannot realize quantum communication. You know, we talked about a classical channel is this decoherence channel. So, you know, when you write a classical channel like this, it's obvious that it cannot send quantum communication. It cannot send quantum information to it. It cannot realize quantum communication. The classical communication alone can't do it. Entanglement alone also can't do it, because entanglement is a static resource. You know, it cannot be used for communication over large distances. It cannot be used for communication over any distance. It's consistent with the non-signaling principle of relativity. So, yeah.
So can we know if a channel is classical or quantum? Is there any way to
Okay.
classify a channel as classical or quantum?
That's an interesting question. So I'm writing a classical channel like this. It's one way of doing it, where there's a preferred basis that is preserved, and all the off-diagonal elements with respect to that basis are gone. That's one way of defining it. Another way is, another more general way is to say a channel is classical if it's entanglement breaking. Okay, so I don't think we've talked about that yet, but we have talked about separable states. So a channel is said to be entanglement breaking if, you know, any state of this bipartite system that you prepare, if the resulting state is unentangled or separable, the channel is said to be entanglement breaking. And so such a channel has no ability to transmit quantum information either. That might be a more general definition. It would be basis independent. Indeed, this channel is entanglement breaking. Okay, this has no ability to transmit one share of an entangled state. Okay? So that's how you can define classical channel. All right. Okay, so neither of these on their own can realize quantum communication, but together, there's kind of this magical way that it gets accomplished. My understanding is that this protocol was discovered. Charlie Bennett was visiting the University of Montreal and presenting some seminar. They had a discussion, and then by the end of it, they had this protocol. They were trying to understand what's called local operations in classical communication. And then supposedly Bennett said, well, what happens if we throw in an EPR pair to what you're doing? And then, they discovered this thing. Okay, so before presenting it, let's recall the Bell states. We've written them before, but I'll write it again. So then let's enumerate these possibilities. Okay, those are the Bell states. And then you can see things like if we add phi 0 to phi 1, the 0, 0 term survives, the 1, 1 term is gone. So those identities are helpful for understanding teleportation. Let's write them. A cheat sheet on the side over here. There's going to be 4 of them. All right, so what is the diagram for teleportation that we like to draw? Okay. So imagine that before anything happens, there's a state of A prime that Alice wants to teleport, and there's an entangled state that Alice and Bob share. So then we're going to assume they share phi 0, 0, also called phi plus. Right. We assume they share this beforehand. Here. Then what? Alice locally does a Bell measurement, right? So that's called local operation. And then classical communication. Okay. So teleportation, I think we'll be studying entanglement theory for a little bit. We'll probably have at least one lecture about that. And in entanglement theory, the free operations are called local operations in classical communication. this is an example. Bell measurement is a local interaction between A and A prime, and then classical communication from Alice to Bob. And then Bob does a local operation at the end. Okay? So this is a particular kind of abbreviated LOCC. So this process, we draw a box around the whole thing. It is indistinguishable from an ideal communication channel. That's what teleportation, that's what you can call the teleportation identity. Okay? And in quantum information theory, we're interested in counting resources. So what are the resources consumed in this protocol? We consume 1 EBIT. Okay? That's also like entangled state, 1 Bell pair, 1 EPR pair, whatever you want to call it. And 2 classical bits. Generate 1 qubit. Right? And in this resource sense, what you can show is that this is optimal. Right? What do I mean by that? Try to do it with fewer than an EBIT or fewer than 2 classical bits. You can't do it. If you try to use, it's related to that, if you try to use just an EBIT and 2 classical bits, all you can send is 1 qubit and no more. Okay? So those are various things that we know. All right, let's talk about why does it work? Any questions about the protocol before we proceed? Okay, so to show why and how it works, well, I guess this is the how it works. We're going to show why it works. We're going to use the state vector formalism. We're not going to use density operators because it's much easier to describe everything using the state vector formalism. Okay. So let's psi A prime. This will be alpha 0, beta 1. This is the qubit state vector to be teleported. Okay. And the initial entangled state will be, let's call it phi. Phi AB, this is a shorthand for phi 0, 0. The initial state, the initial global state of Alice and Bob is this, psi. That's the initial state. I'm going to show you the final result before going through all the steps. You can go through a sequence of relatively straightforward algebraic steps to conclude that this state is equivalent to this. Okay. So you can go through a sequence of steps to show that. All right, the plan is to go through that. Looks like we should have enough time. So how do you go through it? Like, well, we'll do that. So right now, what I want to say is like, once you have this identity, it becomes much clearer why this protocol works. Okay. All right. So why does it work? Well, what have we done? You can view this as this identity is expanding the overall state, and sorry, the systems A prime and A in terms of the orthonormal Bell basis. You can view it as an expansion, right? Like any state, you know, if I have a state, let's say phi AB, I can always write it as if you expand using an orthonormal basis for system A, and then there will be some like phi i's here, right? That you can always do. How do you? What is the? This is like you just calculate the overlap of phi AB with this orthonormal basis, and then you know if this identity holds, you'll get root pi. So what we did here is the same conceptually as this kind of expansion. Okay? Why is that important? Well, I mean, that was probably one of the main insights mathematically. You know, the idea is so simple that it actually makes sense that this be published as in Physical Review Letters, which is where it was published, because you can, math is simple, you can express it there. Okay. Anyway, so the first step of the protocol is for Alice to do a Bell measurement. And so if we've expanded A prime as A with respect to the Bell basis, then we can figure out what are the outcomes. So what would the outcomes be? You know, after the Bell measurement, there are 4 possibilities. The state becomes probability 1/4, right? So it like, you know, reduces to one of these 4 possibilities with equal probability. Or phi probability, and then the final possibility is this. Okay, so those are the 4 possibilities. And then you see the state of Bob's system, if you know the classical data, right? Like Alice knows that the state of Bob's system is one of these 4 possibilities. It becomes one of those 4 possibilities. After the measurement, it definitely becomes one of those 4 possibilities. When John Dowling was alive, he would speak of instantaneous teleportation. We're going to return to that point later. Okay. But here you can see why he used that term, because it's like once Alice does the Bell measurement, the state of Bob's system instantaneously becomes one of these 4 possibilities. So I agree with that statement. You can debate the other point. Okay, so then only with the classical bits can Bob figure out how to undo these Pauli operators to recover initial qubit of Alice's system. Okay, so indeed, if Bob once he gets the classical data, if the bits are 0, 0, then he knows he doesn't need to do anything. Okay? If he gets 1, 0, he knows he needs to do Z, to invert Z. Right? And if he gets 0, 1, he knows he needs to do X to invert the X. And finally, if he gets 1, 1, he knows he needs to do X then Z to invert this. Okay? So that's the basic of how it works. The main thing remaining is we have to justify this identity. I want to say a few more things about this instantaneous teleportation claim. Okay. And I want to make a few more comments about the teleportation protocol. The probabilities of the outcomes, they're uniformly random. They're independent of alpha and beta. Okay? That's very important for the protocol. Okay, so there's no, they're independent of alpha and beta, and so it works unconditionally. No matter what input state is put in here, it will appear at the output. If the classical outcome is dependent, if the probability is dependent on the alpha and beta, then you would somehow be learning about the state that's being input, and you would disrupt it. Okay, that's part of this. We haven't quite talked about it, but there's an information disturbance principle in quantum mechanics. So if you're learning something about a state, then you can inevitably disturb it. Okay, so that doesn't happen here. The other remark is about the claim of instantaneous teleportation. What is the state of Bob's system at this point? What is the reduced state of Bob's system B, the initial point of the particle? Maximally mixed state. Okay, so it's maximally mixed state. What is the state here after the measurement of Alice, before Bob does anything, before he has the classical data? What is the state? Same, maximum mixed state. Okay. There's two ways you can think about this. The Bell measurement is a channel. So a channel is trace preserving. Right? So without the classical bits, to figure out Bob's state here, you should do a trace over these classical systems. And you can think of the measurement as a measurement channel, and it's trace preserving, so the trace propagates. Presumably the way that you deduce that this is the maximum mixed state is because, well, we said this was the maximum mixed state and nothing happened, and so this has to be the maximum mixed state as well. Okay, so that's all consistent. But the point that I want to make is that without the classical bits, Bob knows nothing. There's nothing that's been teleported. Okay, so that's one way to think about it. Consistent with it is Bob's state is randomly, after the measurement outcome, you can think of it as being randomly psi, z psi, x psi, or xz psi. So how do we calculate the density operator for that state? If we have an ensemble, right? So we talked about ensembles and how we calculate density operators for ensembles. The ensemble here for Bob is 1/4 psi. Let me write the density operators. 1/4 z psi, etc. Then the final thing, right? So there's 4 possibilities. So what is the density operator for this ensemble if you don't know the classical data? Yeah. So how would we write it? We'd say, well, it's 1/4 psi plus theta that 1/4 z psi, right? We just wrote down an identity, it's gone now, but we said if you take a random mixture of the Paulis acting on an arbitrary density operator, what do you get? Maximum mixed state. Okay? So the point is that everything's consistent. If you think about it, I think we discussed at least 3 different ways to justify that Bob's state here is maximum mixed. In that sense, you can argue that there's no instantaneous teleportation. Okay. Good. Starting to run out of time. That means that you'll have to verify this identity on your own. It's in the notes, it's in the book. I want to make some other comments. Suppose that there's always quantum information. We think about quantum cryptography. In quantum cryptography, you're paranoid about the presence of an eavesdropper. Suppose there's an eavesdropper here tapping the line. Right? Indeed, the eavesdropper can learn the classical bits, but the eavesdropper cannot learn anything about the quantum state to be teleported. So you have security in that sense. It's only if you have access to the classical bits and this quantum system that you can reconstruct the state that was teleported. Okay? So that feature of teleportation gets used in quantum key distribution protocols. Like there are different variants. I realize we actually haven't even talked about the no cloning theorem. Right? There's something called, this is very important, something called the no cloning theorem. So what it says is that there does not exist a unitary that can do this. Right? That's the no cloning. So what does that mean? We have an incoming state vector. You try to copy it to make another state vector. That's impossible. Okay, that's ruled out by the linearity of quantum mechanics. There are 2 different ways you can argue it. One from linearity, one from unitary. So if you're familiar with the no cloning theorem, you might look at the teleportation protocol and say, well, gee, it seems that you copied the state. It seems like you're violated the no cloning theorem. Okay? Here you reply and say, oh, au contraire. You know, there's a state here, and what happens is that through the Bell measurement and the entanglement, it gets disembodied, right? It kind of gets redistributed. And this is an identity, right? So you can see that through this identity, the quantum information here is getting redistributed, right? And then the measurement happens, and then it gets reconstructed over here. Once it's well, I would argue once the Bell measurement has been performed, the quantum information here is gone. The psi that was here is gone, right? And then it's getting reconstructed over here. So there's no violation of the no cloning theorem like this. The no cloning theorem is about copying quantum information in space, but it doesn't say anything about copying quantum information in time. Right? Like unitary evolution is the copying of quantum information in time in the same spatial location. Right? And so teleportation is this interesting combination of disembodying the state somehow in space and then copying it in time. Right? But it doesn't do anything like this. There's only one side that's reproduced over here, and the one that was here is gone. Right? So that's another point to make with teleportation. We're out of time. So what we'll do next time is talk about this identity, and then we'll talk about teleportation of qubits, d-dimensional systems. And there's even a very interesting, it's beyond the scope of this course, but there's a generalization of teleportation to continuous gravity systems. It's relevant for phonological experiments. All right, so let's stop there. Unless there are any questions. Yes. Superheads coding was a year before, 1992, Bennett and Wiesner. That's an interesting point to make. Let's make it. Superheads coding, the diagram looks like this. First the Pauli's, then the Bell measure. And you have superheads coding, and then you swap the actions of Alice and Bob, then you get teleportation. I'm not sure if that's part of how they discovered it, but you know, it was there. I don't actually know the date of the discovery of teleportation, but publication was sometime in 1993. All right. Yes. Have a good day.